Hello everyone, my name is Thomas Papageorge, and for my 3051 Intro to Structural Engineering Project 3 on structural systems, I will be giving you guys a tour of the East Barbecue Sauce Kitchen additions at Ken's Foods production facility in McDonough, Georgia. For a brief outline of this presentation, I will start with an introduction involving background information on the structure, then cover materials which comprise it, continuing into construction methods. Afterwards, I will be talking about some structural load paths in the building's frame, perform a brief structural analysis of an element in this load path, then cover out with a conclusion statement and references. Located at 155 King Mill Road in McDonough, Georgia, this location for Ken's Foods serves the Southeast United States with staple Ken's sauce lines such as Newman's Own, Ken's Ranch Dressing, Honey Mustard, and Blue Cheese, as well as Sweet Baby Ray's barbecue sauce. The kitchens covered in this tour, outlined in red, are specifically used for cooking Sweet Baby Ray's. This kitchen area on the east side of the complex was originally built in 1999 for use as a warehouse space, though recent expansions in Ken's business persuaded them to convert this space to production. Further works were completed to turn this area into a barbecue sauce kitchen in 2005. Beginning in October of 2020, work began to increase structural performance to further add a walkable ceiling to the structure, additional process chillers on the rooftop, as well as a ceiling-mounted crane for adding ingredients to batch processes. This phase of the project is set to finish mid-May of this year, 2021. Shown in the picture to the top left here, placements for cranes inside of these kitchens can be seen in the drawing. To the right, there's a picture taken from the walkable ceiling, which has recently been installed. And to the bottom left, there's a picture of the rooftop processing units, which are now placed on the structure. For some brief information on parties involved in designing this structural renovation, the head architect is David Rager of O'Neill, and the head structural engineer is Gurmai Megasteb, PE of O'Neill. For information on materials involved in creation of this structure, the external facade of the building is made of 13-inch thick thermal precast concrete panels involving 5 inches thick of concrete sandwiched between two 4-inch thick layers of insulation on either side, coated on the outside with a polymer coating to protect from weathering. The floor of the kitchen area was originally polished concrete in 1999, but since the 2005 renovation has been switched to acid wash brick due to greater resistance to cracking and to eliminate maintenance needed. Interior wall panels in the kitchen are made of FRP or fiber reinforced polymer to replace previous concrete block in order to prevent excessive sealing needed during installation. The kitchens also include a walkable FRP ceiling to access process piping and sprinkler equipment above the production floor. The roof of this structure is made of corrugated steel, topped with insulation and more thermal precast. Finally, topped with rubber mats for safe travel to rooftop process equipment and air handling units. The main load-bearing elements of this structure are made of structural steel, specifically ASTM A992. Structural steel was required to be painted and remain painted after welding due to the corrosive nature of the production environments within the building. For construction details, this phase of the project, once complete, will have taken 7 months. Main difficulties involved in completion of this project have been working while the rest of the plant is still in full operation, resulting in the large plastic drapes which are seen on the screen. Schedule pressures have also been significant during the completion of this project due to the capitally intensive nature of Ken's Foods' production lines. Placement of structural steel for this project and mechanical equipment was done by method of a mobile crane parked on the back access road behind the plant. Though O'Neill was responsible for architectural and structural design work on this project, capital project delivery was responsible for general contracting work with major subs involved, including Action for electrical and mechanical work, along with structural steel performed by BC Steel. For information on load paths in this structure, the structure is designed to take heavy gravitational load from mechanical equipment sitting on the rooftop, as well as the soon-to-be mounted ceiling cranes. As the sides of the building have very large flat walls, it is assumed there's significant wind loads that could also hit the structure, incurring design for rigidity. Movements of fluid and process pipes can also incur a live load on the structure, as with the soon-to-be mounted ceiling cranes. While snow load was accounted for during design of this structure, It was not as significant as at Kansas' other plants, as say Massachusetts or Illinois. Starting from the rooftop of this structure, load from chillers and mechanical units comes down into corrugated steel used for structural elements of the roof. This corrugated steel then sits on joists, as seen in the second picture, which run the length of the structure. These joists then tie into girders, which either run the exterior wall or run perpendicular to the exterior wall into the middle of the structure. Vertical load is transferred through shear in these girders into columns, which then bring load down into the floor. Areas of the load path of this structure which are uncertain include sections of the FRP panels and the walkable ceiling, where it's difficult to see how much the mechanical equipment sits on the walkable ceiling, or how much of it actually ties into hangers that come off of the upper ceiling. For a simplified structural analysis of an element in the load path of this structure, the exterior wall girder for the first barbecue sauce kitchen, here outlined in green, will be examined. A rooftop load of 14 pounds per square foot will be assumed as per design documents. With dimensions of this kitchen taken from previous design documents is 56 feet by 43.5 feet, total distributed load on this section of roof comes out to 36,540 pounds. As half this load is distributed to each girder, and then divided by its length for distributed load, also involving a 68 pound per foot self weight on girder 1, weight on this girder per linear foot comes out to 488 pounds. With this new distributed load mapped on the girder 1 with a fixed condition at either of its column connections, a fixed end moment table yields a vertical support reaction of WL/2 at either end of the girder, with a moment reaction of WL²/12. Plugging these values into actual dimensions of the girder yield a vertical reaction of 10,614 pounds at either support and a moment reaction of 76,951.5 pound-feet. The bottom right-hand corner of the screen here, a shear force diagram and moment diagram can be found. Values off these diagrams will be used in the following slides to calculate internal stresses in the beam and compare it to material properties of the steel used. In the top left-hand corner of the screen, max flexural stress calculations of girder are found to be plus or minus 11,959 psi. On the right-hand side of the screen, cross-sectional and material properties for the element can be found, with a W24/68 cross-section and material composition of ASTM A992 steel. Shear stress calculations in the top half of the page here show a max shear stress of approximately 60 psi plus or minus. When comparing these stress values to material properties of the ASTM A992 steel, it is found that flexural stresses come out to somewhere between a fifth and a seventh of compressive and tensile strengths, while shear stresses are several orders of magnitude smaller than the shear strength of the material. Therefore, it is found that flexural stresses were likely designed for over shear stresses for this girder. In conclusion of this tour for the barbecue sauce kitchen renovations on the east side of Ken's Foods' McDonough, Georgia production facility, it is concluded that structural renovations in this project have allowed for installation of ceiling cranes and additional rooftop equipment to improve production efficiency. It is also found that installation of walkable ceilings allow for easy access of mechanical equipment vital to production processes. At this point, this tour is complete. I would like to thank you all for attending my structural systems tour. I'd also like to thank David Papageorge and Daryl Zuby for assisting me in acquiring information on this structure. And I would also like to thank Paul Darden for allowing me to coordinate a site visit. Listed here are references for information gathered in this project, as well as drawings and pictures, which are used for description and explanation. Listed here are references to numbered pictures, which are used for decorating slides. All facility pictures not cited in these references were taken during a site visit on April 23rd of 2021.